Indirect discharge. This is an electrical disturbance caused by an electromagnetic pulse generated during the flow of the main lightning current. Its duration is quite short, and the energy produced is much lower than the energy of the lightning itself. However, it is a hazard responsible for about 90% of all damage to electronic equipment that occurs during lightning strikes. Indirect discharge from an electromagnetic pulse is referred to in technical literature as LEMP. When lightning current flows to the ground, a strong electromagnetic field is generated around it in accordance with the right-hand rule. The strong electromagnetic pulse generated spreads over a large area around the lightning path. Its presence is detected within a radius of up to several kilometers from the point of lightning strike, and its power depends on factors such as lightning current, discharge duration, and terrain. There is a real threat to electronic devices within a radius of up to several hundred meters, as the power of the electromagnetic pulse decreases with distance from the point of lightning strike. If the propagating electromagnetic pulse encounters a conductor aligned with its vector, a high voltage potential will appear between the ends of the conductor. Its value will depend on the intensity of the electromagnetic field, the permeability of the walls, and the length of the conductor. If the voltage at the ends of the wire rises to a certain value, the insulation of the wire or the electronics connected to it will be broken, and the current loop will be closed through the ground or other conductive materials. The discharge of the energy accumulated in the wire will cause an impulse current to flow, which will result in the overheating and damage of the electronic components of the connected devices. The use of a lightning protection system is an effective solution to prevent fire and the main lightning current from entering the building. However, this does not have a significant impact on the protection of electrical installations inside the building, and even poses a greater threat. The vertical and horizontal arrangement of lightning conductors can transfer much higher energy to the conductors of other installations during a lightning discharge in the lightning rod. Long sections of electrical installations laid horizontally inside a building will absorb little energy from a discharge near the building. A lightning discharge in a building's lightning conductor will cause the lightning current path to run vertically, but also horizontally. The sum of the induced voltage, and thus the amount of energy in the conductors, can be significantly higher and more destructive to electrical and electronic equipment. There are various ways to prevent the effects of indirect lightning strikes in the form of electromagnetic pulses. The same solutions are used for nearby lightning strikes and for strikes to a building's lightning protection system. They should not be used interchangeably, but should complement each other depending on the risks. One way is to shield the cables by placing them in metal trays that are grounded in several places. These prevent the electromagnetic pulse from penetrating the cables and generating harmful voltage in them. Metal cable routes cannot be used everywhere, so another method is to use dedicated surge protectors. They discharge the energy accumulated in the cables through their own circuits, preventing the surge loop from closing through electronic devices. Surge protection devices must be appropriately selected for the rated voltages and types of electrical signals. They must provide a high level of protection, and at the same time not affect the original electrical signal. Galvanic isolation is an effective way to limit damage caused by electromagnetic pulses, as it prevents the closure of the surge loop. Many telecommunications and industrial automation interfaces have galvanic isolation as standard. However, it should be remembered that this is limited in terms of voltage. With long cables, isolation is insufficient and requires additional surge protection devices. Nearby lightning strikes are particularly dangerous for long telephone lines, measuring lines, and control lines located outdoors. Long and thin cables absorb a large amount of electromagnetic pulse energy. but their high impedance causes this energy to be released slowly. To ensure adequate protection, such installations require protectors tested for a voltage pulse with a waveform of 10 to 700 microseconds.